Hi, Bobcats. Let's take a look at vapor pressure. Our objectives are to define and describe vapor pressure, to connect vapor pressure to intermolecular forces, molar mass, and boiling point, and to actually define what boiling point really is. When we're talking about vapor pressure, we are talking about let's see if I can get a pen here. There's a pen. We are talking about the gas phase that forms when you have a sealed container and there is some liquid in that sealed container. Technically, you get vapor pressure for solids as well, which is like why you can smell things like when you smell sugar and it smells sweet because some of that sugar has gone into the gas phase. But for the arguments we'll be making in this section, we're going to be looking at liquids. If you take liquid like the liquid water that is down here on the bottom of the flask, and then you seal it up, right? That's what that stopper is doing up there in the top. What you'll find is that some gas builds up in that volume. We know that gas is there because we see the formation of the droplets of condensation which along the sides of the flask, which tells us that some of that water must have gone into the gas phase, traveled up inside of the flask, and then condensed out on the sides of the flask. All right, so what is this vapor pressure all about? Well, if you look at a particle description of the liquid and the gas interface, what you'll find is that in the liquid part, which is the part below the line in this diagram, let's see, can I get a highlighter or a laser pointer? Yeah, there we go. If we're looking at the liquid portion, which is below this line in the diagram, we've got the particles fairly close to one another, so they are attracting each other with their intermolecular forces. But some of those gas particles have enough thermal energy, or some of those liquid particles have enough thermal energy to overcome those intermolecular forces and escape into the gas phase. So we get the phase transition of some of these liquid particles turning into a gas. Likewise, it is possible for some of these gas phase molecules to turn back into a liquid as they get close to other other particles of the substance. The intermolecular forces cause them to condense. Well, it turns out that there is a fixed amount of where's the pen? There's the pen. There's a fixed amount. Oh, it's not letting me select the pen. Hang on, let's see if we can get the pen. There we go. I think I got the pen now. There we go. There's a fixed amount of the substance that will go into the gas phase. What we're looking at, like let's say this is water, like was in the flask that I took the picture of on the previous slide. We've got H2O liquid. And then we're going to use a funny kind of arrow. It's called the equilibrium arrow. When you're reviewing any of this at the end of the semester, you'll know all about equilibrium. But basically what happens with equilibrium is that we reach this steady state where there's a fixed total amount of water in the liquid phase and a fixed total amount of water in the gas phase, but the particles can keep exchanging. So at some point a liquid molecule will evaporate and go into the gas phase, and somewhere else in the flask some of the gas phase water turns back into liquid phase water. So the total amount of water in the liquid phase and the total amount of water in the gas phase remains constant. If you think back to Gen Chem 1, when you studied gases, you talked about Dalton's law of partial pressure and the physical origin of pressure, right? Pressure is the force exerted by the gas phase particles as they hit the walls of their container. And Dalton's law of partial pressure tells us if we have a mixture of gases, each gas independently exerts a pressure, and in order to get the total pressure in the container, you add up the partial pressures of all of those gases. Okay, so when we reach this equilibrium state, the pressure exerted by the water in the gas phase is referred to as the vapor pressure. It's that steady state pressure. Just trying to connect this back to intermolecular forces. Remember that that process of evaporation requires that the molecules in the liquid phase have enough energy to overcome all of the intermolecular forces so that they can separate and go into the gas phase. So we see some connections, like if you have stronger intermolecular forces, you're going to have a lower vapor pressure, because if the intermolecular forces are stronger, fewer gas particles have enough energy to overcome those intermolecular forces and go into the gas phase. And conversely, weaker intermolecular forces give you a higher vapor pressure, because if there's not a lot of force holding the particles in the liquid phase, more of them can escape to the gas phase. Another really important point to make about vapor pressure is that vapor pressure increases with temperature. Let's think about that for a moment. As the temperature increases, the kinetic molecular theory tells us that the motion, the speed of the gas particles increases. So you have more kinetic energy, more particles at higher temperatures can overcome the intermolecular forces and escape to the gas phase. So as the temperature goes up, the vapor pressure goes up. And last but not least, one vocabulary word that is often misunderstood is volatile. Volatile refers to a temperature with a high vapor, or I'm sorry, a substance with a high vapor pressure, because that means that it's going to evaporate very easily. Volatile is not the same thing as explosive. Explosive has other meanings associated with it, like it's very sudden, heat is usually involved, it's a sudden hot release of gas that rapidly expands. So volatile just means that a substance has a very high vapor pressure, and so it evaporates easily. All right, let's take a look at the next slide. This chart is a set of vapor pressure curves. It's showing for on the vertical axis what the vapor pressure of a substance is, and on the horizontal axis what the temperature is. So you can see clearly here that as the temperature increases, we move to the right on the graph, the vapor pressure of a substance increases as well. There's sort of a magic point on the vapor pressure side, which is when we hit 760 torr. 760 torr is the same thing as 1 atmosphere. So that's the pressure that we normally experience. And let's take a look at the water vapor pressure curve at 1 atmosphere. So if we go over all the way to the blue water curve and we look at the vapor pressure, or we look at a pressure of 760 torr or 1 atmosphere, we're looking at this point right here. Turns out that point coincides with a temperature of 100 degrees C. So what do we know about water at 100 degrees C? Well, at 100 degrees C, that's the boiling point of water. So the vapor pressure of water, when it equals 1 atmosphere, that gives us the boiling point of water. That is actually a general statement. Any substance, or a better way to say that would be, we can generalize that statement. Any substance will boil when its vapor pressure is equal to the applied atmospheric pressure. And if the applied atmospheric pressure is normal atmospheric pressure, 1 atmosphere, 760 millimeters of mercury, we call that the normal boiling point. So adding that word normal has a specific connotation. Normal means the temperature at which the substance boils when the pressure applied to the substance is 1 atmosphere. So this has some interesting implications. If we follow this curve to lower vapor pressures, so for instance, let's say we drop the pressure, we're looking at when is the vapor pressure of water dropped down to something like 200. So if we drop down to 200, which would be here for the vapor pressure, right? Vapor pressure being 200 torr, the temperature at which it's the vapor pressure equals 200 looks like it's between 60 and 70 degrees. Just for the sake of argument, I'm going to say 65. So this is saying that if we reduce the pressure on our water sample to 200 torr, that water is going to boil at 65 degrees. We see this in the real world a little bit less dramatically. If you go to high elevations, so if you travel to Denver, the mile-high city, water will boil at a temperature less than 100 degrees. Because water is boiling at a temperature less than 100 degrees, you sometimes have to cook things a little bit longer, because if you're cooking something in boiling water, like spaghetti, the temperature is not quite as high, and so the cooking process doesn't go as fast. So actually, let me just go on to the next slide to look at this, because it's all spelled out in words on the next slide. Boiling point is defined as the temperature at which the vapor pressure equals atmospheric pressure. So whatever your ambient applied pressure is, the boiling point is the temperature when your vapor pressure matches that. Normal boiling point is the temperature when the vapor pressure is equal to 1 atmosphere. And normal boiling point is the type of thing that you will see in tables if you look up the boiling points of substances. All right, one last thing. Take a moment and go watch this video on YouTube. It's really pretty amazing. It shows you water boiling at room temperature because it's being done in a vacuum chamber. It's really kind of cool. There's also a really good argument in there about water or about boiling being an endothermic process because once the water starts boiling, the thermometer that's stuck in the liquid water shows that the temperature drops, because as the water molecules go from the liquid phase to the gas phase, they are taking thermal energy from the water molecules that are remaining behind in the liquid phase, and so the temperature of the liquid water drops, and it's really pretty dramatic watching all of that. All right, let's take a look at our next slide. Let's take a look at the vapor pressure curves for water and ethylene glycol. That's the blue and the green curves. Water, of course, is HOH. Ethylene glycol is a 2-carbon chain, and each one of the carbons has an OH group on it. Glycol is a term that implies an alcohol with 2 OH groups. So ethylene glycol is the 2-carbon version of this. I want to compare these two molecules because they have different molar masses and they both are capable of doing hydrogen bonding in 2 spots. We've got essentially two OH groups. On water, we would consider that to be one OH group and then that to be one OH group. We're using the same O for both, but we've got 2 spots where these molecules can do hydrogen bonding. And notice that ethylene glycol with a bigger molar mass has a lower vapor pressure. If we've got similar intermolecular forces, that tends to be generally true, that if you have a bigger molar mass, you have lower vapor pressures, and then that's with lower vapor pressures, that means you're going to have to go to higher temperatures to get a vapor pressure of 760 torr or to start boiling. So generally, higher molar masses will have higher boiling points. Let me make sure I correlate all of that correctly. Higher molar mass means lower vapor pressure and higher boiling point.